We discussed in the previous section how to evaluate a machine learning model from the side of trying to look into how do we break down the data? How do we arrange the data? We spoke about the leave one out and also the cross validation. So, however, when you talk of evaluating machine learning model, it will not be complete if we don't talk about the performance measure that you can actually check in this particular machine learning building procedures. So as we are building the machine learning, what are the important machine learning performance measure that you need to look into? And then this also depends on the kind of problem we are solving. So that is why we are going to look into the performance measure for classification models. Then after that, we're going to discuss the performance measure for regression model. That the regression model is when you are predicting actual values, as you are going to see later, that you want to predict the student score. So what is going to be your final mark? So is it going to be 95.5, or in this final exam out of 40, what is going to be your score? That is regression. But when I'm predicting if a student is going to pass or fail, that is classification problem. So classification is often the simplest one and the common one, while regression is a little bit more tasking, but then it's also common, especially in engineering for problem solving. So let's look into what are the performance measures that when you want to evaluate machine learning, what are the performance measures you have to look into? So either you are using the leave one out partitioning method, or you are using cross validation. Either of the two or three you are using, definitely you need to check for some of the performance measure that will determine or that will show you if it is time for you to stop training your model or you still need to continue. Now, so on the description of classifier error, describing classifier error. So one way to check or to evaluate, to determine how the model you are building is performing is to actually describe the error. So because the error is going to be opposite to the performance. I mean, if the error is huge, that means your performance is bad, it's low. So that's why some people call it error analysis or classifier error description. So how can we check the amount of mistake the model is making? So if the mistake is very, very few, then that is fine. It means the performance is great. But if the mistakes are so many, then you know that your model is not performing. So that is why we often talk about description of classifier error. Now, to start from the simplest, the one we call the binary classifier. Binary classifiers, these are model built to classify problems into yes or no oriented problems. Like I have data set from the clinic and I want to predict if somebody is diabetes. It's going to be yes or no. So we call it binary classification problem. And the model build will be referred to as binary classifiers. Now, so that a model is going to be a binary classifier or multi depends on the kind of data set you have. So if your data set is a multi-class problem, then the outcome of the modeling is going to be multi-class classifier. However, if it is a two-class problem, then it's going to be a binary classifier. Because majority of the algorithms, they have the capability to classify into multiple classes. With the exception of very few, like support vector machine, that does not have direct binary classification, it doesn't have direct multi-class problem solving, but however, there is a way to bypass it and still solve it using the same support vector machine. So which we are going to discuss, one of the algorithms we are going to discuss hopefully soon, inshallah. So, so considering this, so when we have binary classification problem, for example, in a construction company, maybe in the civil engineering field, we want to predict if a particular bridge might collapse or not. That is yes or no. See, so that's a classification problem. We are not predicting the strength of that particular bridge, but we want to predict, is it likely going to collapse or not? If our prediction says that, oh, this bridge might collapse after some time, then it is the next stage is to have a predictive model for the regression. How many years or how many months is going to take before this bridge comes down? So you can see we can have multi-stage predictive solutions. The initial stage is to determine if the bridge is going to collapse, or let's say house. Is there any possibility that this particular house is going to collapse? If yes, then predict how long it's going to take before it actually comes down. So, and then if you do that, you can move to the next level. Is it likely going to come with casualty or otherwise? I mean, there are so many problem solutions that could be provided by these multi-stage predictive solutions, depending on the problem we are solving. So now, starting from the simple one, or the simplest one, we call the binary classification problem. Here, you only have positive or negative. So somebody is going to be diabetes. Diabetes patient is going to be positive. Negative means he is not diabetes. Now, to describe the performance of these kind of models on binary classification problem, what do? We have what we call the true positive. Then we have what we call the false positive. And then we have what we call the true negative. And then we have what we call the false negative. These are the four categories of kind of prediction output we can have. So what is true positive? So to understand this true positive, false positive, we're going to move to the next, which we call the confusion matrix. Confusion matrix will make it clearer and easier for you to understand how to be able to differentiate between the outcome of your experiment when you are evaluating models. Now, for now, just know that true positive means the original output is true and your developed model actually predicted it to be true. Maybe a particular patient is diabetes. So when you put the data of that patient into your model, it predicted it to be diabetes. So it means it was correct. We call it true positive. However, false positive means the data fed into your system actually belonged to someone that is presently not diabetes. However, the outcome of your predictive solution says that your model predicted a person to be positive, which means it's saying that person is positive, is diabetes, even though it's not diabetes. So in that case, we say this is a false positive. That is, the outcome from your model is a positive prediction, but that prediction is false. It's not correct. The model just succeeded in predicting someone who is okay as not being okay. Now, so then the other one is true negative. That is, the data entered to your system for prediction is for a patient that is not diabetes. This person is free of diabetes. And luckily, when your the prediction from your model also says negative, it means, oh, congratulations, you are not diabetes. It means the negative prediction you have given that you are not diabetes is actually correct. We call it true negative. It means the negative prediction is actually true. In similar way, we have what we call the false negative. It means the person given to your model for checking is actually a diabetes patient. However, your model ended up saying, no, you are not diabetes. You can go home and enjoy. We call it false negative. It means the negative prediction is not correct, it's false. So these are the four different categories of predictive value you can have. Now, these two, the true positive and the true negative, they are the correct one. These are the one we are looking for. We always wish to have this because they are the correct prediction. It means you are able to identify the diabetes guy, you are able to identify the non-diabetes guy. No error. However, these are error cases. False positive is a mistaken prediction. False negative is a mistaken prediction. However, when we move to the actual cost of misclassification, the cost of the error you are making, this thing can be different depending on the area you are modeling. False positive can be more serious in some area, whereas in another area of application, it could be false negative that is more serious. As we're going to discuss this now, let's move on. So once you know this value, these four values from your predictive solution, then you can then calculate the other ones, like recall. Recall is you just use this as true positive divided by true positive plus false negative. Precision, true positive, you can see true positive and false positive. You can see the difference is this false negative. This one is false positive. We're going to discuss this one also later on. So one is a measure of the false negative rate and the false positive rate, how accurate it is and how correct is this. And the other one is also the F measure, which is trying to combine recall and precision in an equation to be able to see to go, how was the general measure of the system? So depending on the area that the application is coming from, we have some area whereby the F measure is their most important one. However, the most important one to know is what we call the confusion matrix. The confusion matrix is very important because this is going to give you the opportunity to break down your predictive outcome in a very clear way. And then if you're developing for client, this is how you can be able to really know the actual cause of mistakes that your model is making. Because yeah, mistakes are mistakes. We don't want any mistake, but sometime in life, there will always be mistake. As it is often said, without mistake, people cannot learn. So the same thing in machine learning also, sometimes machine learning make mistake, but what is the mistake that is welcoming? Some mistakes are welcome, it's okay. But some mistakes, they are no. For example, somebody is sick, you say it's not sick. That your predictive model is serious, it's a big mistake it's making. Because the person might go home, start living normal life only to get the chronic aspect of the disease because the machine learning model has failed to identify him or her correctly. So we say in that case, false negative is a serious mistake in medical prediction. Now let's look at the confusion matrix. Let's pay attention to it as the name. I still don't know why they call it confusion matrix because sometimes it could be confusing. So let's pay attention to it. We have the true positive, the one we mentioned. We have the true negative, sorry, the false negative. Then we have the false positive, and then we have the true negative. Now, this diagonal, the right diagonal, this one, they are the one we want. These are the what we look for. These are the correct one. This guy and this guy, they are correct. These are the mistakes. Now, this one, as you go here, this is the prediction from the model. This is prediction from model. These are the actual values here. Across is the actual value given. That is, so these are the actual value given to you that from this side, these are positive results. Anything in this area, in this line, they are positive from the original data that you are given. However, vertically, these are the outcome from your predictive solution. Now, so these are everything in this line, they are positive according to the original data. However, in the predictive solution, the outcome of your model, it predicted these values to be positive, even though they are also positive. So this is why we call them true positive. However, in this column, sorry, in this cell, this value is originally positive, as you can see here. This is the true given value. These are the predicted here. So this one is originally positive. However, our model predicted it to be negative. That's why we call it false negative. False negative means true values that are predicted to be negative. So we say that negativity prediction is false, it's not correct. Now we move to negative. Negative, those are those, if we are working on diabetes patient, those patients that are not diabetes, we call them negative. So these are the negative data. Everyone in this row, they are negative. However, you can see here, as well, let me start from this. Here, you can see negative, because negative, our machine learning model predicted this one to be negative. We say this is true negative, because the original value given, they are negative patients, and our predictive solution also predicted them to be negative. We say this is true negative. It means the negative prediction is correct. Now move back to the false one. You see, originally these are negative samples, but our predictive solution put them to be under positive. You can see it put them to be under positive. That's why we said this positive predictive outcome is false. It's not correct. So it means this cell and this cell, they are the mistake that we do have in our outcome, in the outcome of our modeling. Now when we talk about, so having known what is true positive, true negative, false positive, false negative, then it now depend on the actual cost of error. Now, You see, these two, they are the error. This is the mistake. False negative is a mistake here. False positive is a mistake. However, let's use this example as diabetes or in medical. If somebody is sick, confirmed to be sick, but we didn't know, we are using machine learning to do the screening. So the machine learning predicted that person that you are not sick, you are negative. So we say false negative in medicine. In medical application, false negative is a serious mistake. False negative is serious. We are not saying false positive is also good. We don't want any mistake, but some mistakes are acceptable. It's like when you have two evils, you have to go for lesser evil. Yeah. So false positive for medical prediction is a lesser evil. So, but for false negative, you are predicting that someone is not sick. Meanwhile, that person is sick. So you miss the prediction. So the person will go ahead, enjoying himself, doing normal thing, only for him to suddenly fall into coma. It could be even as simple as you think diabetes. Somebody just fall into coma, only for them to go to the hospital and they say, oh, the sugar level is too high. And he never knew. And he will say, oh, but I've been using my machine learning system to check myself. That means that machine learning system is having very high rate of false negative. So we don't want this kind of mistake in our medical prediction. In this sense, if I have a model that is having 98% accuracy, another model with 97% accuracy, however, the mistake for these 98%, they are all false negative mistake. But for these 97, they are all false positive mistake. We are going to go for this one. We will select this one as our final model for medical prediction. Why? Because the mistake of this one is a lesser mistake. That is, somebody is not sick, but you predicted the person to be sick. Of course, you can create some panic in the patient, but the patient will go to the clinic, get tested as a follow-up, and then they will say, oh, you didn't have any diabetes. Congratulations, you can go home. Of course, he or she might have wasted some money or some time, and the panic also induces a prediction. But then when you compare to the cost of someone who has been ignorantly informed that you are negative, meanwhile, it's already suffering from the disease, we can see that the false negative is a serious mistake compared to the false positive. So that is why when you are actually evaluating your model, after you train and test, so it's not just enough to check the accuracy of your model, you need to go into your confusion matrix to see where are the mistakes coming from. That's why sometimes you can have 98% accuracy. In fact, you might have to go in for as low as even 96%. If all the mistakes from 98 are all false negative, and all the mistakes from 96%, they are false positive. Okay, we better have 96% false positive accuracy than going for that false negative. For example, like glaucoma, like the medical practitioner knows better, where the nerve that connect the eye to the brain keep getting caught gradually. The person can just lose his own total eyesight suddenly while driving. Maybe that's the last nerve that is connected. So because of false negative prediction. So it could be dangerous. Imagine such scenario. So that's why in medical, we don't tolerate false negative. So we might have to say, okay, that's why if you work on your model, there was an earlier result published that achieved 98%. Now you are trying to beat that accuracy, but you couldn't beat it. You were able to achieve 96. If you know how to present your work, you can still get your work through. Because if you find out that the mistake from these guys, they are all false negative, but your own new model was able to avoid false negative mistake by having only false positive mistake, you can still be able to convince that, yeah, this is what I've contributed by avoiding the most costly mistake. Because the cost of mistake also matters, not just 20 mistake. We ask you, where is the mistake coming from? Is it the costly side or the cheaper side? Now, in similar fashion, if I'm using another model to predict for production company, let's pay attention to this. You see the opposite now. There's a company like maybe it's like Lissabi or any company that produces some goods for their customer. So after the production, usually they run a machine learning algorithm, which has been developed, a model developed to check if the quality of the product is good or not. So you know here also we're going to have positive. Positive means good, negative means not good. See, you know, if in medicine, we don't want false negative. We say this is no. However, in production company, what they don't want is false positive. They don't want false positive. False positive is serious. It's a serious mistake in production companies. Why? Because false positive is going to tell the company that this good is okay. You can send it to the customer directly. Then they will send it to the customer. Meanwhile, it's a false positive. It's not good. So when you get to the customer can take the company to court, and you can know the implication, especially in this age of social media. You could take the company to the social media, blackmail the company, tell them a lot of things, don't buy things from them. Things like that could happen. So as a company, we don't want false positive. Rather, we can tolerate false negative in production processes. False negative means a good has been produced, ready to go for to the customer. However, our machine learning system says, no, this good is not good. It predicted it to be negative. So the company need to delegate another human control agent to go and check physically, to double check what is wrong with that good that the machine learning system is saying it should not go. After double checking it, they now find out that the good is okay. There's no problem. It can go. This is false negative, but this false negative is a problem that is not big. We only wasted a little hour of some of those quality control experts by double checking to prevent us from sending wrong goods to our patient, to our client or our customers. So what this entails us is that, so the false positive is not a general rule. Somebody will say, what is false negative? False negative is bad. False positive is bad. No, it depends on the area you are modeling. So in production processes where they need to produce something for their customer, they don't want any mistake. Let's get it right. However, if there is going to be any mistake, they can still manage first negative, because that will make sure that they double check before they send it to their customer. Unlike false positive, that will make them to send false good that is not good to the customer, and that will land them in a big trouble. So we can see the opposite now. For medical, false negative is no. But for production companies, false positive is no. So when you're developing machine learning model for your client, so you have to look at the client you are developing for and determine, talk to them, which mistake can you manage? Or do you think this mistake is still negligible? So this is when you're evaluating machine learning model. So it's not just enough to say the accuracy. Sometimes you might have to go into especially the final model you are building to be deployed for your client. You go into the confusion matrix and try to check for yourself what are the implications of the mistakes that we are actually making. Now, so having said that, so this is what the accuracy, which is the popular one we mentioned, is the total number of images that are objects that are correctly classified divided by the test total samples you have. That is the accuracy we popularly talk about. Accuracy. How many total correctly classified? And when you talk of total, that is true positive plus false positive. Sorry, true positive plus true negative. Those are the correct one. True positive plus true negative, divided by the sum of the four. True positive plus true negative plus false positive plus false negative. All the four outcomes we already mentioned to us, we put them as the denominator. This is going to give us, multiply by 100, that will give us the accuracy of your model. So when you divide it, if you are getting like 0.98, so times 100, that's going to be like 98% accuracy. Okay, so but I'm saying sometimes it's not enough. You might have to look into your confusion matrix to really understand the actual cost of the mistake, because except when you get 100% accuracy. If you get 100% accuracy, it means everything is working perfectly. Both the negative class and the positive class, they are all correctly predicted. Then in that case, you can relax, because there's no false negative problem. But if you are getting 90% accuracy, it means there's an error somewhere. You need to dig deeper by going into your confusion matrix to see this 2% error that I'm having, where is it coming from? Is it coming from false negative or false positive? Which company am I modeling for? Is it a production company that does not like false positive? Or is it for medical that doesn't have, so is it the production company does not like false positive, or medical center that doesn't like false negative? So you have to analyze it, then that will guide you when you are evaluating your classifier to be able to evaluate correctly. Now, sometimes when you have multi-class problem, so we have several classes, like you are trying to classify, let's try to classify different type of DNA. See here, these are the actual value, these are the predicted value. This is output from your classifier. These are the true classes. You can see. So you have 98 DNA are predicted to be DNA. These are true positive for this guy. You can see other mistakes. 0, no mistake. So at the end of the day, at this diagonal, these are the true values, the ones that are correctly predicted. So you're going to find the average of this because this is a multi-class system. Then finally, if you find the average, you find out you're going to have like 98% accuracy. This is how the confusion matrix for multi-class problems looks like. Now, so model evaluation continues. So once we build our model, partition the data as we have mentioned, let's say, for example, here, let's demonstrate the true positive, true negative we're talking about to bring life to it. Yeah. Let's look at this together. This is you want to predict. This is the hypothesis. This is predicted value. This is the output. Remember, we mentioned hypothesis function H of X. So this is the predicted output from this is from the model. But this is the actual class that was given to you. This actual class provided for you. So provided in the data set from the industry or from the hospital. Now, so the original value is, there's a decision here for we want to predict if a student should buy a computer or not. So the outcome here is to buy. Our outcome, our model predicted buy also. So we're going to call it, there is no error here. This is true positive. Because buy. Here, the outcome, the original output is buy, but the prediction is that you should not buy. This is negative prediction, and the original result is to buy. So we're going to have here, this is the one we call false positive. Because, sorry, this is predicted value. The outcome is to buy, which is positive. Our prediction is that we should not buy. So we are having false negative. Yeah, false negative. There's an error here. That error is a false negative error. That's what we say. There's an error here. Now, the next one says the actual value given to you is not to buy, which is a negative value. But our predicted value is go and buy. There's an error also, but that error is false positive. You predicted positive to go and buy, but the answer is supposed to be negative. Then so you continue like that to fill the table. Here, there's no error here, but this is going to be true positive also, yeah, because buy. Here, don't buy. These are two true negative. This is true positive. So here is you need to buy is the predicted value. Meanwhile, the original one is this one, which is similar to what we have done here. This is also false negative. Why this one is also true negative, because there's no error. Both the output given in the data and your predicted value, they are also the same thing. Here also, this is true positive. And then this is also true positive. Here, don't buy, that is true negative. So we fill this one for our confusion matrix. So you remember true positive, true, false positive, true negative, and then false negative. So you now count it. How many true positive do I have? You put it in this hole. How many false negative I have? You put it in their respective hole. This is how you can formulate or you can get your true positive, true negative. The good thing is that any modeling application you are using, like Weka, will automatically tells you the value of will show to you the confusion matrix. So you don't need to do it manually, but we show this to you so you can also understand how the system works. So these are, for example, like the example given now, you can see here, you can see here we have the true positive, and then the value are fixed in there appropriately. So once if you look at it now, you can see here, this is 4 plus 3, that is 7. So you have accuracy of 7 divided by 10. That's like a 70% accuracy, if I'm not mistaken. So 70% accuracy. There are two mistakes. There's a mistake of 1, there's a mistake of 2. See? But this mistake, this is the true positive mistake. Sorry, false positive mistake, and this is false negative mistake. So these are the two mistake pin box we have, the cell. So that is when you use machine learning to evaluate your classifier. Now, then, so this is what we've explained, because we always talk about error. Since the data set might be many, let's imagine you have like 1 million data set. So that's why you don't count the number of correct classification, but you count the number of errors. That's why majority of people prefer to go with the error, and that is actually what we do in the modeling. You calculate the error of the hypothesis, which means what is the difference between the given value and the one that you are predicting. You find the difference, you calculate them. So the error is 3 out of 10, which is 0.3, which is 30%. When you take 100 minus 30%, that's going to give you 70% as the accuracy. So the opposite of the error is the accuracy. Now, so that is on the confusion matrix as one of the very important evaluation performance measure for checking your model. Another point to note is, the false negative, depending on where you are applying it, people do call it type 1 error, where this one is called the type 2 error. See, so when we have the positive predictive value, and then we have the recall, which is the negative predictive value, depending on the problem we are trying to model. In addition to this, is that there's a couple of different interpretation of some of these systems before we move on. We have the accuracy, which is given. We have the error. I've explained that. We have the true positive rate, or the sensitivity, or recall, which is something you need with the recall is that it's asking the metric question, how many of the positive does the model return? And precision is about how many of the return documents are correct. Maybe you're searching on the web. So this is the difference between the precision and the recall. So in some application area, they pay more attention to the F measure, and F measure is what? But the harmonic average of precision and recall. So our mathematician knows that, can put more effort, more light to that later. So what is the harmonic average of the precision and recall? We want to see how many of the positive the model is returning, vis-a-vis how many of the return positive are actually correct. So at the same time, so you want to find the average. Now, having done with the simple, these are just examples for those classification. These are just simple slotting. Once you get your confusion matrix, the good thing is once you get your confusion matrix, that's very small box. You can solve any other F measure, precision, and the likes, depending on the case. Now, so a point to know about the F measure, say the higher the precision, the lower the false positive. So this is the interpretation of your precision. The higher the precision, the lower the false positive. The higher the recall, the lower the false negative. Whereas the higher the F1, the lower the FP and false negative. So that's why F1 is like an average of the two. It's trying to measure the two simultaneously. So if you can get higher F1 value, it means both false positive and false negative, they are manageably very low. However, if your F1 is very high, it means you can have recall that is high and precision that is low. Then that F1 will go down because the precision will affect it, and the other way around. You only get very high F1 if the two sides are balanced somehow. That is, none of them is higher. It means you're almost approaching 100% accuracy. Now, so this is when you look at the multi-class confusion matrix, as I've mentioned example before. This is another example of multi-class confusion matrix. Now, something I will have to mention is it's not just enough to just measure, in addition to checking the confusion matrix, which is very, very important. If you know how to describe, how to discuss your result from confusion matrix point of view, it will really help you in presenting your work very well. And it shows the performance of your model in a very clear format. However, other things to look at is what we call the precision recall curve. So these are often automatically generated for you from the system you are using, either you're using Python, Weka, and the likes. But what is the essence of this? Yeah. So See, we use precision recall curves to check. Especially we need it when the classes are not balanced, imbalanced class. When we say imbalanced class, I think I've explained one time. Let's say you have a data set given to you. You have like 50 samples, only 50 samples. After the 50 sample, you have 25 diabetes patients and 25 non-diabetes patients. This is a balanced data set. Usually, this is what we want in machine learning. If the data set is balanced, this is excellent. We celebrate it because our model is likely going to get good results or excellent results. However, in real life, we don't have this kind of data in most cases. Because if you go to the clinic, maybe out of 1,000 patients they are having, maybe it's only 250 of them that are diabetes patients. The remaining 750, they are non-diabetes, negative. You can see that the negative class is more than the positive class. This is the reality of the world. In most disease classification, you have more class than the other. So this is called class imbalance. Class imbalance. So when you have class imbalance, accuracy is not enough for you. Accuracy will not tell you the correct implication. If you can have class imbalance, if a model is not able to classify one of the classes, you might still be getting very high accuracy. So you'll be deceiving yourself thinking you are getting good result. Meanwhile, it's only predicting one class. It's not able to separate the other class. I'll give an example just shortly, as we are going to see. So precision recall is one of these ways that we try to see to tell us how the system is doing. Let's look at this example to show the limitation of accuracy, that you cannot just use accuracy to judge. Let's say we consider a two-class problem. The class 0 has like a 9,990 samples, and the number of class for class 1 is just 10. So this one might be okay, non-diabetes patient, and this is diabetes patient. Only 10. Now, if you develop a model in this kind of data, this is very imbalanced data. This is going to be a problem. If the model predicts everything to be class 0, let's take notes. We run the model trained, because there are so many of these, it was able to recognize who is class 0, but was not able to recognize anyone from class 1. So it predicted, so when you tested it, it predicted all of them to be class 0. That everything is class 0. So in that case, accuracy is still going to be total number of the prediction that you have gotten, which is, you see, what you're going to get, you are going to get 990. That is, it's able to recognize all the class 0. However, it couldn't recognize anything as class 1. No single class 1 recognized. You know, in the correct classification, all of them have been predicted as class 0, which is the whole 1,000 data has been pushed to be class 0. But remember, our accuracy is correct classification. So out of this 1,000 pushed to class 0, 9,990 will be correct, divided by the total, which is 1,000. So, sorry, 10,000. So, which is going to give us 99.9%. So you can see that you are going to get 99.9% accuracy, even though the second class is totally 0. That is a very bad model to train, because the model couldn't recognize class 1. So this is the issue of using only accuracy. Because anybody checking the accuracy, oh, you will start celebrating. Oh, I got 99.9. But then you are not really doing anything. Out of 2 classes, you are pushing everything to class 1. So to the first class, you are not able to recognize the second class. So this is where accuracy could be misleading. So that is why once you have accuracy, the next thing you quickly check is check your confusion matrix. Confusion matrix don't lie. Confusion matrix will tell you that in the true negative here, you're having 0. You are not getting anything from this class. Then you know there's a problem. All the data are pushed to this side. 1,000 here, 0 is 0. There's a big trouble here. So you know that you have a very big problem. Of course, you are going to have like 10 here. So it will show you there's a mistake. You are predicting one side, you are not able to predict the other side totally. So this is why, to avoid this kind of false assumption that your accuracy is correct, you need to go for that, to use what we call the receiver operating characteristics. You have to plot it. It will tell you if there is a balanced prediction between the two of them. See, that are they able to predict correctly? For example, if you have multi-class problem, so see what we want a perfect system. A perfect system is going to be very close to the wall when you plot it. But when you see something like this, okay, it's still a little bit manageable. But we want something that is closer to the line, like this. The closer this curve is to the line, the better the classifier you are getting. And our resource will even make it even more clearer for you to analyze. So receiver operating is, which is going to measure the parameter at the various threshold of settings. This to show, to really check if your prediction is random or it's not random. See? So if you have a prediction like this, that show you have a prediction like this. This is like 0.5 area under the curve. You're going to have area under the curve. Okay, you're going to have area under the curve. That is like random prediction. Random prediction. So we don't go for that. But rather, the closer your curve is to the top, actually, we want something that is very close. The perfect one is to have 1 here. It means the more this one curve go up, then it means your model is performing. However, because of our time, we hopefully stop at this level. So let's just assume that, okay, we clarify very much the idea of using the the precision recall to show us, especially when you have imbalanced data set, the precision recall curve will show the trade-off between the precision and recall for the different threshold. And it is often used to really tell us, okay, if you are having imbalanced data, the curve will show that there's a problem. Because if you're having 99.9% accuracy, with 99.9% accuracy, you expect to have a perfect curve. But then you are going to see that the curve is not going to be perfect. That will show you something that, no, something is wrong. One of the classes is not being presented, it's not being accurately recognized. So this is why we don't stick with only accuracy, but rather in evaluating our model, we have to combine it with other measures, as we are going to see. Now, we've talked about confusion matrix. Use it in conjunction with your accuracy to really see where the mistake is really coming from. Also, we have the precision recall curve. We're going to have the ROC. And then after that, we are going to talk about the area under the curve. And then we are going to move to the regression problem, where we tell you also how you can evaluate your model there to check that your model is really doing fine, using the root mean square error, the correlation coefficient, and especially using the appropriate plot where necessary. So these are some of the things, inshallah, we're going to have a look at, inshallah, by the grace of God, next week. So we're going to call it a day at this point. So thank you very much for listening, and we wish you really all the best. So barakallahu feek.